I'm quite happy today to talk about the third code release from lowRISC. Actually, it's a collaboration between lowRISC and SoC Debug. So in this time, not only we bring up the updates from RISC-V Berkeley team, we also bring up a new trace debugger. So right now, you can use the lowRISC untitled SoC to generate instruction traces and analyze the performance and finding bugs off-chip or, well, maybe at runtime. For anyone who doesn't know lowRISC is a not-for-profit community project providing complete open source SoC designs. We aim to provide open source hardware. So in a way, it seems like Linux for the hardware world. We aim to offer complete SoCs that can run Linux quite well. And we hope the SoC platform is kind of extensible. So this allows the lowRISC SoC to be the base design, allow other people to do further designs to make some products based on it. And lowRISC is a founding member of RISC-V Foundation. We use RISC-V cores like we use Rocket cores, and we hope to use the Boom cores in the future. And currently, we plan to use the Palpino cores as the Minion cores. We plan to do volume runs on silicon, and we plan to do low-cost development board for hobbyists and for other people to use it. And we plan to release reference designs to help other people to use lowRISC as a base design to do their products in a way like it's a RISC-V for grown-ups. We also have our own research focus. We hope to use the tag memory and Minion cores to boost the security and the flexibility of current SoC platforms. The core team currently is located in Cambridge, the computer laboratory of University of Cambridge. We hope the lowRISC platform can be used by everyone, so we adopt a simple and permissive license. That basically means it's free to use for anyone. It's open source, it's free, there's no cost to use code. And we adopt the active community collaboration, so we are kind of open for anyone who want to talk with, use it, and even contribute with it. We plan to do regular tape out in a way that we can verify the contribution from community to check the IP is right, and in a way to encourage everyone to contribute to lowRISC. The Minion core is one of the two technology point we want to add. We hope to use Minion core to do flexible program I/O and to do performance counters, accelerators, and to do some security code processor. And to use the tag memory to do some boost the security and use tag memory as performance monitors, synchronizations. We have some initial fund from a private donor, and very thanks to Google that we got donation from them to staffing some people. And eventually, we hope to be self-sustained. In previous RISC-V workshops, we have two code releases. The first one is tag memory, and the second one is untagged SoC. So this time, we add in trace debug on it. And as I mentioned, this release is a combined release between with lowRISC and SoC Debug. SoC Debug is an umbrella project which provides unified debug infrastructure. It's hoped to provide shared building blocks, interfaces, and tools among different platforms in a way that to reduce the effort to adopt this infrastructure in different SoC platforms. To reach the scale, so the SoC Debug uses an abstract level of host interface connections. So it uses the glib library. You can use any cable you want, like USB, JTAG, UART, or Ethernet. Then this abstract glib library will provide an abstract layer. So on the host program side and on the SoC side, they see the same interfaces. You don't need to worry about what kind of cable is used. And all the debug modules are modular designed, so you can choose what kind of components you're going to choose. You can have configurations to say, use this module, do not use that one. It's totally configurable. And we use a uniform on-chip communication networks. So the network doesn't necessarily mean you have maximum number of components on the network. You can configure the network in a way you want, even different topology in the future. So the functionality right now we provide is a trace debugging, but in the future we hope to provide run control debugging like a normal GDB support. Suppose I need to explain what's the difference between trace debugging and the GDB, the run control debugging. So trace debugging is not run control debugging. It doesn't stop the processor. It doesn't generate a breaking point. You can't stop it. But the benefit for that is it's kind of running simulation using the real hardware. You can generate the traces. You can extract the instruction trace from your real FPGA run. It's kind of non-intrusive. And it doesn't generate it's kind of minimum performance overhead. So what it do is actually to extract the instruction sequence from your processor, filter it, only extracting the information that is enough for you to generate the whole trace offline. And the benefit of using trace debugging is that sometimes you can't find some bugs by using run control debug. For example, if you run in multi-core, if there's a racing conditions, there's a timing issues, you can't really stop the processor to find out bugs. So in this case, you are better off to use the trace to find out the bug off-chip analysis. And also, trace debugging can use as a performance evaluation. You can find how this processor, this SoC is running slow. You can't really do that using the run control debugger. So it's also kind of way to do lightweighted instrument in your system. This is the overall structure of the current release. The blue part is all chisel designs from Berkeley. Yeah, and based on the last release, we add some I/O devices and DDR3 controller there to make the whole SoC untethered. This time we add the trace debugger, which is the pink part. If we show that part in detail, so that's how we do it. So we have a lot of modular design as the pink components inside that. The host PC is connected to the trace debugger using a host interface and using the glib library. So basically, you can use whatever cable connection you want. In every Rocket core is a core trace and the software trace. The core trace will extract the instruction trace from the processor, and the software trace is somewhere users can define what event you want to trace from the processor. So users can use in program special instructions to trigger some events. And all these traces will send to the debugging ring network. Then this information will go to the host interface and send to your host computer. And there's a memory access module which allows the trace debugger as a program loader. So you can use the trace debugger to load the program, whatever program you want, into the cache, into the on-chip boot run. And also it replaces the UART connection with a serial communication. Therefore, you can share the UART cable with your trace information. At the same time, there's a console you can control the processor. The system control module will generally reset because sometimes we want to load program, we want to stop the process running. As we want the trace debug to be kind of easily adoptable for different SoCs, so we don't know how many debug modules are currently existing in the network. So the trace debugging will using an enumeration process to figure out how many processes, how many tracing modules currently in the system. There's only 2 modules must be existing in the system. One is the host interface, otherwise you can't connect into the SoC. The other one is system control. You always need a reset facility there to pause the processor. Also, the system control module will have the total number of tracing components in the system. After you get this total number, then you kind of try to figure out how many modules inside the system, as every module has its own register set. They share the same set, so you can find out, if you find a module, you can tell what's the function of the module from this preset register. Then the system control module is, one function for that is you can tell how many debug modules are currently existing in the system, and you can send a comment to the system control module to pause the processor, allow you to load data to the L2 cache or load data to DDR3 memory. The memory access module is basically give the trace debugger a way to load the program you want to run to the system. Before that, you stop the processor. Then the memory access module will give you access currently to the L2 coherent bus. And then you can load your program. As I mentioned, the serial communication is kind of emulate a UART IP, and it allows you to give you a console at the same time to send the trace information using that cable. The function of core trace is try to extract the actual instruction traces from your processor. The usage for that is you are enabled to reconstruct your program flow from these traces. I will show some examples afterwards. Currently, it's only extracting information for function calls, jumps, but in the future, we hope to extract information like load and store, like special instructions if any instruction being trapped, and allow you to set different filters to filter whether or not you want this information to be extracted to the host computer. Because we want to reduce the total number of events sent to the computer, the bandwidth for that trace or on-chip tracing network is kind of low, so you don't want to send everything to the host computer. You probably need some dynamic filter settings here. After these instructions has been generated, after these events have been extracted, then they will send to the debugging network in a packet. As the on-chip debugging network is packet-based, the network is kind of modular. Here shows you an example core trace, which you can extract in by running a very simple program. Basically, here is what's the preparation before the main function. And in the main function, there's just very simple functions to generate trace event. I believe that's a software trace. And after that, you can see that the main program just exists, and there's some traps to make sure the process is stopped. And this missing event is because when the process is hot, there's an infinite loop to it. It loops itself to stop the program from processing any further. So that's a lot of events. I recycle this event, then the internal buffer will overflow, kind of. We hope to kind of reduce this problem to generate filters, so then in that case, you don't see this overflow. The trace, the software trace is another mechanism allow users to trigger events by using special instructions, but actually it's not really special instruction, it's a special CSR. The benefit for that is sometimes we want to debug, we will send some information to the console. We want to show some variables, but that is heavy weighted, as every printf function will cost you hundreds of cycles. With this, you can send out value to the console by using only a couple of instructions rather than hundreds of instructions. So it's a very lightweighted way to replace the printf function. And this has minimal performance impact, as every time you print out something, it's only a couple of instructions. To do that, every user-defined event is a pair of ID and value. The ID will say what kind of event it is, and the value will show what value you really want to read from the real processor. The value, currently the software trace will constantly monitor what value being written to A0 register. Once you write that value to A0 register and write a special ID to CSR, there's a special trace debugger CSR, then this write to CSR will trigger an event. And because the software tracer is always constantly monitor the value write to A0, these two values will combine together, generate a trace, and send to the host computer. That's how the host computer will receive this information. And here shows a quite interesting example how you can use the software trace to figure out something. These two lines shows how you can generate a trace. Basically, you write this trace as a macro function. And the first line is say write a value to register A0. Then immediately the second instruction say write a special CSR, write a special CSR with the trace ID. And this instruction will trigger a trace along with the value right in the first instruction. Then you can use the space macro functions to build your own more complicated trace function. Like this one is trying to say when there's a buffer being allocated in memory, I want to know the start address of the buffer. And this one is if there's transaction on this DMA, I want to know what's the source address, what's the length, and what's the target address. And the final one will tell you when this DMA transaction is finished. So in this example program, let you first allocate a memory space for the DMA. You will know the address of this buffer. Then you do a DMA transaction. You will know what's the source of the target and the length. And after that, you will know when the DMA transaction is finished. And in your host computer, you will see this event by this trace, which is a software trace. And you get all the times. Depending on the ID, you will know what kind of event is that. And this value will tell you like the addresses or the length. Or I think you get the idea. Here shows you how you can use the trace debugger. So here is a console that you will get on the host computer. Basically, at first, you need to stop your processor. That is reset hot. Basically, it's a general reset signal to stop your processor. And hold this reset, therefore, the L2 is in the total control of the trace debugger. Then you can load whatever program you want to load into the on-chip block RAM or to the DDR RAM by using this memory load function. Because the tracing system is kind of modular, so you don't really know where this memory access module is. The daemon will tell you which number, which module ID it is. So here it tells you that memory access module has a number 3, so you put a 3 here. Then you know how to load the program to the L2 cache or to the DDR3 memory. And this one will enable the call trace. So you say enable the call trace using this log comment and log the comment into this file. Also, we know that the call trace module is number 4 here, so we put 4 here. The second line, this line is kind of enable the software trace. Also write software trace to this module, and we know the software trace module is number 5. After that, we can, this one is initiate the console, so you get UR's window there. You can input some comments, and you see the printf come out, and then you start processing. Also, a benefit for that is currently we support all these functions in a Python script. Therefore, you don't need to actually write in those comments in the console. You can actually write a program to do that automatically for you. Another benefit for that is because all the things are wrapped up in the Python function, so you can write more complicated debug GUIs, programs to do the things automatically. There's some extra interesting features for this debugger right now. It's not only running for the FPGA runs, we have the same infrastructure for simulations because the UART support and the glib library is also implemented in behavior level using DPI C interface. So you actually get the same infrastructure both in the simulation and in the FPGA runs. This allows you to compare the traces in simulations and in FPGAs to make sure it is running okay. And because the Python front end, so you can incorporate this trace debugger into more complicated tools. For the future, currently the trace only tracing certain events, and the traffic is kind of high. So in the future, we want to generate kind of runtime configurable trace filters that allow you to change the filters to choosing what events will be going to be extracted. And we will implement some control flow in on-chip tracing networks to allow reduce the time of overflow and allow some information get higher priority. And also we have an idea like using minion cores to processing the trace online, so therefore we don't need to send everything to the host computer to analyze off-chip. In this code release, we have two kinds of boot procedure. The first one is the title one, so you can use the trace debugger to load your program into the FPGA's on-chip block RAM or to the DDR RAM. Also, we provide untitled way, so even you can disable the trace debugger, then the system is wholly just an untitled standard system. You can use a program in the on-chip block RAM as the first stage bootloader. Then this bootloader will store the Linux kernel from SD card to the DDR memory, then jump to the DDR memory, run in the Linux kernel. And here shows you where you can get this code release, and we also have a tutorial just like a previous release. You can see how to run this demo on the FPGA and how to utilize all these functions. We are choosing to use the lower end board, the Nexus 4 DDR board. And we have the latest updates from Rocket chip up to June this year. Also, the whole environment is free right now. It's still like last time. We don't use any commercial tools like VCS. The only thing you need is a board, the Nexus 4 board, which gives you a free license to run the FPGA softwares, and we use a Revelator, which is total free. And we also provide a full set of makefiles and a strip like last time. We have 3 releases right now. The next time, I think we will bring up the tag memory back to the low-RISC chip. And we plan to integrate the minion cores using the Popino cores to do some interesting job to trying to do program IOs. I hope this kind of implementation will finish at the end of this year. So here is an update generally from low-RISC. In this summer, we are very lucky to get some funding from IMC to support 4 intern students to do a video acceleration. So hopefully after this intern finish their job, we could connect a LCD screen to low-RISC board to have so you can see something rather than just using a host computer. And we also have 5 students working on the GSOC project working on some very interesting software and hardware projects. We got a new RA working for us, currently looking for the minion core concepts that hopefully we can connect the Popino cores to low-RISC platform in this year. And thanks to Philip from Grace University of Technology, he has managed to add the tagged memory back to the untagged chip, so I can use that and do some optimizations to re-add tagged memory back to low-RISC. And we have Clifford currently working on the implementation of shim designs. Here shows you the structure of the task chip. Compared with the current release, this part, the minion core part, is the major difference. So we really hope the new RA will finish this work to connect to the Popino cores and minion cores, as that will open up a whole story, a whole space of new ideas to this platform. And we hope to finish our RTL designs at early of next year, and then after that to tape out test chip. I think I'm here really to say that low-RISC is an open source project, so we are really eager to talk with anyone who wants to know low-RISC and to know RISC-V, anyone who wants to learn how to use this platform, anyone who wants to use this base design to build their product, and anyone who wants to contribute to low-RISC and RISC-V. If you have any ideas, just talk to us. This time, not only me, we have 2 of the 3 co-founders of low-RISC coming already. One is Alex and one is Robert Mullins. Probably can you stand up, please, so people will know where you are and talk to you later. Right, I think we have all the communication, the ways for contacts here, so that's it. Thank you.
All right. Thanks, Wei. Do we have questions for the low-RISC team?
Yeah. Hi, Wei. I had a question on the timestamping. So how are you handling clock domains with different...
sorry, it is kind of...
The timestamping on the trace records, how do you handle different clock domains?
Yeah, it's a very important question. Right now, we just use the timestamp, and because the whole SoC using a single clock, so it's not a problem. But in the future, we hope to use the wall clock, the global real-time clock, and sharing some, using that to broadcast some timestamps to all the processors for they share the same timestamp.
That's really, looks like Dave Patterson, UC Berkeley, it seems like really useful. Have you, apparently debugging interfaces are security holes often in architectures. Have you thought about security implications of the debugging system?
Okay, I think you are thinking about people can use this debug infrastructure as a backdoor. And the thought is, well, we don't enforce the using of this debugger. So as I said, you can disable the debugger after you kind of finish your developing cycles. You can remove the debugger there in your configure file, so there's no backdoor there. Also, there's a possibility that we can allow some settings. Once you finish the initial booting procedure, you can write that register to totally disable it, non-existent.
Have you used the traces for like memory consistency checks for multi-processor systems? Could that be done, collecting traces from the interfaces on the buses?
I think your question is related whether or not we can use this infrastructure to collect information from memory systems. As the debugging system is modular design, so yeah, that's in the plan. We hope to generate some debugging components hook up with the coherence bus, and you can extract information from that bus. Maybe help you to understand the consistent issues there. Yeah, it's definitely in the plan. Right now, there's no. We only extraction trace from processors.
All right. Any other questions? That's it? Okay, thank you, Wei.
Cheers.